Welcome to AP Chemistry at Hononegah High School. Today we'll be looking at our first part of Chapter 16, dealing with the first few sections. Chapter 16 deals with acids and bases. We started with acids and bases back in Chapter 4, and we're really continuing on with this chapter. We're still going to add to what we did and also get into equilibrium as it relates to acids and bases. Now, this is one of the major sections on the AP test for the multiple choice. 10 out of the 75 questions each year on average comes from acid and base ideas. So you're looking for something that is a major importance for the AP test in terms of multiple choice. And it's also just about every single year a part of the FRQ, because when you're dealing with equilibrium, a lot of times they'll slide in some Ka, Kb stuff. So this is one of our major chapters to help prepare for the AP test. And of the remaining chapters, it's probably our longest overall chapter. So Chapter 16, we're looking at acid and base chemistry. Now, just as a quick review here, remember acids are substances that taste sour. They turn blue litmus red. Bases would be things that are bitter, and they would turn red litmus blue. These are ideas that you should have looked at last year in pre-AP. And one of the things about acid-base chemistry is it's a water chemistry chapter. When you're dealing with acids and bases, what you're dealing with is situations where these molecular substances or ionic substances thrown in water cause water to behave as either an acidic or a basic solution. Now, one of the earliest definitions of acid-base behavior was by a scientist by the name of Arrhenius. Now, Arrhenius, you should recall from a couple of chapters ago when we got into the delta E, the energy of activation, and the relationship to K. It was the Arrhenius equation, same scientist. So Arrhenius was one of our earliest people to come up with a chemical definition of what was acid behavior and base behavior and why. Now, we'd known about and named things, acid and base, before this, but this was the first person to really understand. I mean, because we'd known citrus fruits tasted sour and so forth, and we had certain things that were like them in behavior, and that came from, I believe, it's the Greek or Latin acidus, and the idea of base. Certain types of plants, when you burn them and create an ash, put it in water, make the water bitter and basic in nature. So the idea of acid-base predates Arrhenius, but Arrhenius was really the first person to put a chemical explanation behind what was going on. Arrhenius basically said an acid is a substance that when dissolved in water increases the concentration of the hydrogen atom. Now, or of the hydrogen ion, I'm sorry. Now, when you remember water is a polar molecule, the O part of the water is slightly negative, and when you put an H plus by it, those two things would attract. So H plus would piggyback onto the water, and you end up with a hydronium ion. So when we say hydronium ion, what we really mean is an H plus attached to a water molecule. And in many situations we use H plus and H3O plus to be interchangeable, but typically when we're talking about hydronium, we're talking about H3O plus. So anything would increase the concentration of the hydrogen ions. In other words, things that have hydrogen ions in them would be considered an acid. And a base was a substance that would dissolve in water, would increase the concentration of OH minus. So any substance that had hydroxide in the formula would be considered a base. So that's our earliest definition. If you got a hydrogen, you would be an acid. If you have a base, you would have hydroxide. Therefore, you put those things in water, you'd increase the H plus or the OH minus concentration of water. And fundamentally, if you remember from pre-AP chemistry, what we're really looking at here is an equilibrium situation. Water self-ionizes, which means water molecules can collide and create H3O plus and OH minus, but based upon the stoichiometry here, for every one H3O plus, you get one OH minus, so these concentrations would be equal to each other in a neutral solution. And it doesn't ionize very much. It's really at normal temperatures, 25 degrees Celsius, it's really only about 2 in a billion actually ionized. So we're talking about a very low concentration, but it does exist and it is there. And if you had H plus in an equilibrium situation, that would cause this concentration to go up, shifting equilibrium in that direction, and that would cause OH minus to go down. And that's basically why acids, when substances that have H plus in them to donate, make water acidic, because they make the H3O plus go up and the OH minus go down through equilibrium. On the flip side, what Arrhenius realizes was that things that had hydroxide in them would cause the OH minus concentration to go up, shifting equilibrium to the left, which would cause your H3O plus concentration to go down, making the water a basic solution. So really what we're looking at here is an equilibrium situation that we're going to talk about a number of different times in this chapter. So Arrhenius really had our earliest and simplest definition. If you have an ionizable hydrogen, you're an acid. If you have ionizable hydroxide, you're a base. Now the problem with Arrhenius theory is there were substances that really couldn't explain why they would make water acidic or why they would make water basic. So Bronstedt-Lowery, two scientists, so this is not like Gay-Lussac when you talked about gas laws. These are actually two different scientists, proposed at around the same time a similar idea to explain acid-base behavior that really worked with explaining more substances than simple Arrhenius definition was. And what they Bronstedt-Lowery did was they looked at an acid as a proton donor. So acids were proton donors. Now what is a proton? Well, a proton would be H plus. Remember, hydrogen, your most stable, normal version of hydrogen has one proton, one electron. So if you lose your one electron, what you're left with is a proton. So H plus is a proton. So if you're a proton donor, you're an acid. And then the base would then be the thing that accepted that proton. So a base would be classified as a proton acceptor. So in the case of HCl and NH3, HCl was something that Arrhenius definition had called an acid. It has an ionizable hydrogen. So we knew from Arrhenius definition that HCl, hydrochloric acid is an acid. Well, ammonia didn't really fit Arrhenius definition. It doesn't have a hydroxide, but yet when you put it in water, it makes hydroxide. It makes OH. So ammonia was something that Arrhenius theory couldn't adequately explain, but Bronstedt-Lowery theory works very well. So remember, by Bronstedt-Lowery theory, a Bronstedt-Lowery acid would be a substance that has a removable proton. It's a proton donor. So HCl would give its proton to NH3 at that point right there. Now the electrons stay behind, so what we're really ending up with here is Cl minus. All of its electrons are still there. So literally, when it leaves HCl, it's leaving as a proton, an H plus. And the NH3, that unshared pair of electrons that's circled right there, that H plus is hooking up at that spot. So this is an example of what's known as covalent coordinacy. Covalent bonds are when one substance does it or donates both of the electron pairs. So this is a coordinate covalent bond that's forming here. So what's happening is NH3 is accepting the proton, and therefore it's acting like a base. And what you end up making is NH4 plus, forgot to put that plus there, and Cl minus. So in this particular reaction, HCl has the hydrogen to donate, so it's giving the hydrogen, and NH3 is accepting the hydrogen, it's acting like a base. So by Bronstedt-Lowery definition, HCl is behaving like an acid, and NH3 is behaving like a base. Now, some substances can act either like an acid or a base. Sometimes they donate a hydrogen, sometimes they accept a hydrogen. An example of that would be HCO3 minus. HCO3 minus can become H2CO3, which would mean it's accepting a hydrogen, or it can become Cl3 2-, which means it gave a hydrogen. So this is a substance that is amphiprotic. It can both give or accept a hydrogen. HSO4- can do the same thing. It can become H2SO4. It's receiving, acting like a base, or it could become SO4 2-, it would be giving, acting like an acid. And finally, water can also do that. If water accepts and is acting like a base, it's going to form H3O+. And if it donates a hydrogen, acting like an acid, it's going to yield OH-. So these are all substances that, depending on what they're with, can sometimes give a hydrogen and can sometimes accept a hydrogen. So sometimes they act like acids or bases. Now, what happens when an acid dissolves in water? Well, remember, water acts as a Bronstedt-Lowery base when you put it with an acid because the H in HCl is going to be going to the water. So in this particular case, water is accepting, by Bronstedt-Lowery definition, it's behaving like a base here. And you end up with Cl- and H3O+. So effectively what you do is increase the concentration of H3O+. So by Bronstedt-Lowery definition, Acids make water acidic because the acids are donating a hydrogen to the water to make H3O+. Increasing the hydronium, decreasing the hydroxide, you have an acidic solution. So as a result of this substance, we end up with two substances here. Now these are both conjugates of the substance above. A conjugate is two things that differ by a proton. HCl became Cl-, so these two things would be conjugates of each other, and H2O became H3O+. These two things also differ by a proton. So this would be the conjugate of H2O, and Cl- would be the conjugate of HCl. So as a result, the conjugate base of the acid and the hydronium ions are formed. So what we end up forming here are these two substances. Now Cl-, the reason we're calling it a conjugate base here is it could be accepting that proton to make HCl in a reverse reaction. Now the term conjugate comes from the Latin word which means conjugare or join together. So conjugates are two joined things, one on the reactant side, one on the product side. Two things that differ by a proton. So NO2 and NO2- differ by a proton, so this is the conjugate base of that acid. And why is it a base? Well, look in the reverse direction. Notice we've got a double arrow here. In this particular case, in the reverse direction, the hydrogen from H3O+ would be going to the NO2-, so this is acting like an acid. In the reverse, this would be receiving the hydrogen. It'd be acting like a base. So on the flip side, this is the product side, this is a base and this is an acid. And these are conjugates of the acid and base on the other side. So NO2- is the conjugate base of HNO2, and H3O+ is the conjugate acid of H2O. Notice conjugates always come in acid-base pairs. So in a Bronstedt-Lowery definition that's reversible like this, you're always going to end up with acid-base pairs. And this would be the conjugate base of that acid, and this would be the conjugate acid of that base. So a part of Bronstedt-Lowery definition is looking at what the reactants do, and if it's a reversible reaction, realizing that they're going to make conjugates, things that differ by a proton. Well, if it's a reversible reaction, those things can also act as acids and bases in the reverse direction. Now, one of the things that you should understand is the relationship between a substance and its conjugate in terms of overall strength. Strong acids, remember, are things that completely dissociate, and you need, in particular in this chapter, to memorize your strong acids and strong bases, because it's a whole lot easier to memorize the strong than it is to memorize the weak, because there's a relatively select number of strong acids and a relatively select number of strong bases. Everything else has to be weak. So make sure you know your strong acids. You got to know that for this upcoming test. Well, strong acids would be things that, remember, completely dissociate in water, so 100% break apart. So up here on top we have HCl and H2SO4 and HNO3. All those things were in our list of strong acids, and that basically means they ionize completely. They ionize 100%. They totally break apart into H+ and an anion. Now, if you have a strong acid, the conjugate of that strong acid is going to be a very, very weak base. So the stronger the acid is, the weaker its conjugate base is. The weaker the acid is, and remember, weak acids are things that only partially dissociate, but the weaker the acid is, the stronger its conjugate base is going to be. Now, in general terms here, when we're looking at these weak acids, right here, things that dissociate only partially, their conjugates are going to be weak, but remember my basic statement a second ago. The weaker the weak acid is, the stronger its conjugate base is going to be. But they still form a weak situation. It's going to be a double arrow. They're going to partially come back and form an acid when you throw those weak bases in water. But there is a relationship between the strength of an acid and the relative strength of its conjugate. The stronger the acid, the weaker its conjugate base is going to be. So the stronger the base, the weaker its conjugate acid would be as well. So substances with negligible acidity, those are things that really don't dissociate in water. So something like H2CH4, they just don't dissociate in water. OH-, it doesn't dissociate in water, it stays as OH-. Those things have negligible acidity. So if you throw them in water, basically water is going to stay neutral, pH 7. their conjugate bases then would be extremely strong. The weaker the acid, the stronger its conjugate is going to be. So the weaker those acids, because they don't dissociate, the stronger their conjugate base is going to be. Now, in any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So this is kind of a guiding principle behind what we're looking at here. So keep in mind what that really says. In any acid-base reaction, the equilibrium will favor the reaction that moves the proton to the stronger base. So you have bases on each side, and in each case you're going to be moving a proton to that base. Which reaction is favored, to the left or to the right, is going to be based upon which one is moving the proton to the stronger base. In the case of the reaction that we have here, HCl is giving a proton to H2O, and H3O plus is giving a proton to Cl minus. So this is acting like a base, and this is acting like a base. But you'll notice Cl minus, negligible base property, H2O would have to be stronger than that. It's right here. So it's right on the border. So in this particular case, the reaction that's going to be favored is the one that moves the proton to the stronger base. That would be the water in this case. So notice what we have here is a single arrow reaction. When you have a strong acid, it's going to ionize 100%. It's going to create a negligible weak base that's not going to go back in the other direction. So this thing is terrible at receiving protons, is really what it comes down to. So these things right here are lousy at receiving protons. So they do not function very well as a base at all. So that means the equilibrium is going to lie so far to the right that we don't even have a measured K for this. It would be incredibly large. In other words, it's not a reversible reaction to any great degree. Taking a look at a second situation here, remember the same idea. What we're going to favor in terms of equilibrium is the movement of the proton to the stronger base. Well, if you take a look at what's happening, it looks like this hydrogen, and I know that because I'm looking over here at what that thing becomes, its conjugate. That hydrogen is going to the water, so that means water is acting like a base here. And on the flip side, that hydrogen is going over there, so this is acting like a base here. In fact, it's the conjugate base of that weak acid on the other side. And I know this is a weak acid-base reaction because I see double arrow right there. It's my dead giveaway. It's going to be a weak situation. Strong acid, single arrow. Weak acids and bases, double arrow. Now, if you take a look at the strengths of our two bases, remember, water's right here. We looked at that a second ago. And acetate, which is C2H3O2, is right there. Which one in this particular case is going to be the stronger base? Well, that would be acetate in this particular situation. So you would expect equilibrium to favor the left side because this reverse reaction is more likely to happen. So that's going to push equilibrium to the left, and that would cause the K value to be small, less than 1. So if this is better at pushing its proton, because this is better at receiving it, than what's happening on the other side, then the reverse reaction is going to be bigger than the forward reaction. And when we are at equilibrium, that means we're going to have more reactants than products. So we can use this relative strength and acid base to understand a little bit about what's happening with equilibrium and equilibrium reactions. Now, as we mentioned earlier, water is something that's amphoteric. And pure water has really a few molecules that act as a base and a few molecules that act as an acid. And that's that idea I talked about from the very beginning from pre-AP, that you have water molecules colliding with each other and to a very small extent creating ions. Now, like I said, it's only about 2 in a billion, but it does happen. And most people say that water does not conduct electricity, and that's something I routinely use. Well, honestly, what would be better is to say that water barely conducts electricity, and for a long period of time it wasn't even measurable. It's really only got better instrumentation that we realized that water does auto-ionize. Because remember, if you create ions that are mobile and can carry electrons, you will conduct electricity. So to a very, very, very small degree, water auto-ionizes, which means to a very, 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 very small degree it does conduct electricity. What we typically say is, when we're saying water doesn't conduct, is that it's so small it's negligible. Now, This is something that heavily favors the reactants. This only happens to a very small degree. I mean, if only 2 out of a billion are autoionizing, it's not happening at an incredibly high rate. And it also means that the reverse reaction is going to happen very readily. So no molecule in water really remains ionized for long. The reactions are extremely rapid in both directions. So at any one time, we're really looking at about 2 parts per billion that are actually ionized here. So this actually heavily favors the reactant side in this particular situation. Now, for this particular reaction, the K for this process is going to equal the hydronium times the hydroxide concentration. And we're going to call that Kc. So this, because we're talking about concentrations here, where that's a Kc. Well, Kc has another name. It's also Kw. So the K of water is basically the Kc of water. And in this particular case, at 25 degrees Celsius, you only get 1 times 10 to the negative 14th. So it's a very, very small quantity. But this idea is one of the ideas in the chapter that you need to be comfortable with and you need to be able to use. So the ion product of water is basically dealing with how much water ionizes. Well, if you actually find out what the concentrations are and multiply them, you get 1 times 10 to the negative 14th, a very small number. Now, one thing to realize, remember from our equation, basically it was 2 waters on this side, and you end up with H3O plus and OH minus. So this basically autoionizes to a very small degree. Remember, by stoichiometry, for every one of these, you get one of those. So these 2 concentrations are equal to each other. So for a neutral solution, these both equal 1 times 10 to the negative 7th. And that's an idea that we're going to be using in future chapters. And that ends the first part of our notes on chapter 16.